Welcome to the WERA 103 presentation today. We're pleased to have Dr. Bryan Hopkins presenting some of his research and some of his experience with enhanced efficiency fertilizers. My name is Rob Mickelson. I work with the International Plant Nutrition Institute, and I'll be the host of the presentation today. Let me give you a brief introduction about Dr. Hopkins, and then we'll jump in and let him begin his presentation. Dr. Hopkins is a native of Idaho in the United States. He did his undergraduate work at Brigham Young University in Utah and then left for Kansas State University where he received his PhD. Dr. Hopkins, after finishing his graduate work, was a manager for a large soil testing lab in the Midwest of the United States. Then for a number of years, he was a professor at the University of Idaho. And then in 2007, he returned to Brigham Young University, where he is currently a professor working in soil science and agronomy. So Dr. Hopkins has a wide range of experience in his work, both in the field and the laboratory and the greenhouse. And we're really pleased to have Dr. Hopkins representing WERA 103 and making this presentation today. So with that, I'll turn the screen over to Dr. Hopkins, and then we can begin the presentation.
Thank you, Rob. I'm pleased to be able to teach this today. I'm going to be talking about enhanced efficiency fertilizers, focusing on nitrogen and phosphorus. Suppose we start with a definition, and I'll keep it simple and not give a full definition, but essentially, enhanced efficiency fertilizers are fertilizers or additives that we use for improving nutrient use efficiency, as well as minimizing environmental risk. So why nitrogen and phosphorus in particular? Obviously, these are a majority of global fertilizer use, along with potassium. We have a lot of problems, though, with these two in the environment in particular, and with uptake. We do have inefficient uptake. It's very common to have extremely low percentages of fertilizer phosphorus that's applied that ends up in the plant. Nitrogen is similar, although not as extreme. We also have some serious environmental issues with air and water quality. With nitrogen, we have air quality issues with regard to reactive nitrogen, which is ammonia that volatilizes, as well as nitrous oxide, which is a very potent greenhouse gas. Both nitrogen and phosphorus negatively impact water quality. In terms of nitrogen getting into drinking water, it can be a problem and is a major concern in that way. And then also, both nitrogen and phosphorus impact water quality in terms of eutrophication. So we'd like to get more of the fertilizer that we apply, the nutrient, end up in the plant and less of it lost to the environment. And one way of doing that is using enhanced efficiency fertilizers. I think it's really critical for us to understand the nitrogen cycle and phosphorus cycle too. I'll start with nitrogen, but if we understand the cycle, it allows us to better understand how and when these fertilizers work or don't work. And so it's imperative to spend some time on this. If we apply fertilizer, a commercial fertilizer, it's typically applied as most commonly urea, but also as ammonium or even nitrate forms. If we put on urea, it converts fairly quickly to ammonium, which then converts to nitrate, or we apply nitrate. And the bottom line is that we have these two compounds, molecules in the soil, that either one can be utilized by plants. And the problem, though, is that both of them are subject to losses to the environment. In the case of applying urea, as it converts to ammonium, there's an intermediate step of ammonia gas. And unless we're careful, some of that gas, or all of that gas, can be lost to the atmosphere, and we call that volatilization. Of course, ammonium itself can also revert back to ammonia and volatilize. We also have leaching losses that is a concern with nitrate. Nitrate, unlike ammonium, is negatively charged. It's also highly soluble, and therefore it moves through the soil fairly readily and can escape the rooting zone and enter drinking water supplies. We also have a gaseous loss in the case of nitrate. We call it denitrification, and that's the conversion to nitrous oxide and similar molecules that end up in the atmosphere. And any one of these forms results in loss, and we don't get the nitrogen into the plant. It represents both an environmental contamination as well as a waste for the grower that paid good money for the fertilizer. I'm going to spend some time here just talking about ammonia loss. The reality is ammonia loss in most situations is usually the biggest source of loss. There's lots of studies that have been done. This is just a sampling of a few that we have. And one of the things that we need to understand is that there's all kinds of conditions that affect how much ammonia you might lose. And these studies all have different conditions, different temperatures, timings, soil pH, soil texture, even the type and amount of previous crop residue, and all those things would affect ammonia loss as well as other loss mechanisms. In these studies, we're looking at urea or urea ammonium nitrate, shown here as UAN, ammonium sulfate, shown as AS, or ammonium nitrate, shown as AN. Not every study measured all or used all of these, but as we look at these studies, we can kind of see the various percentages of loss of the total applied as in terms of volatilization. So we look at this first study. We can kind of key in here and see some pretty big differences in terms of nitrogen loss to volatilization. If we look at ammonium nitrate, it's fairly low, although 5% still is a big number. If you think about that from a grower's perspective, that's a lot of loss. And if you survey the research, these numbers are not uncommon. It's pretty unusual to be less than 5%, and common to be in the 5 to 15 or even 20% of loss. I'm always a little surprised at how much nitrogen we do lose to volatilization. But in this case, ammonium nitrate was our least loss. If we look at ammonium sulfate, it's basically double. And what this tells us, and no surprise, if we look at ammonium sulfate, that's about 100. That is 100% of the nitrogen in that fertilizer is in the ammonium form, whereas ammonium nitrate, only half of it is. And the nitrate isn't really subject to ammonia volatilization. Of course, it's subject to other losses, but we're just focusing on ammonia here. So kind of no surprise that we have less loss with ammonium nitrate because we have less total ammonium. If we shift over here and look at urea ammonium nitrate, we are having significantly more loss. We've lost about 1/5 of the total nitrogen that was applied. Now, in this particular study, this UAN is applied as a liquid, and there's a fair amount of straw residue on the surface of the soil, and the UAN was broadcast applied, which isn't necessarily a good management practice, especially if things are warm. That UAN gets, some of it gets captured on that straw residue, held up away from the soil, and as a result, it's more subject to volatilization. And so in UAN, half of it is in the urea form, and then that's going to convert to ammonium with that ammonia as an intermediate step. And then, of course, 25% of the fertilizer is ammonium. So we have a high percentage of nitrogen that's subject to loss, and we've got just the perfect conditions to lose it. So we see a very high rate of loss. The urea, we didn't lose as much, although it's still pretty high. And the reason is this was applied as a dry product, and it hit the soil. The soil is able to capture that a little more efficiently than if it's sitting up on the residue. So bottom line is we've got a whole range of losses here in this particular study. I'm going to go through every one of these studies, but of the fertilizer in the ammonium and the nitrate form, more of it being captured by the soil, whereas with the urea and the conditions in this particular experiment with nitrogen applied in June, we lost half of the nitrogen. Now it's fairly extreme and one of the higher numbers that we see in the literature, but it is possible to do that. The warmer it is, the more humid, the more the wind is blowing, if it's sitting up on the surface, the more likely we are to lose nitrogen. If we can get it into the soil, we lose less of it. So we talk about using enhanced efficiency fertilizers for nitrogen in a way to try to get more of it into the plant, less loss. Divide these up into two. We have slow and controlled release fertilizers, as well as inhibitors and stabilizers. With the controlled release, these are nitrogen released by a physical process, and we have a variety of products here that, and I've tested almost all of these, and others have as well. I'll spend a little more time on these later. We also have slow release products. These are released by a chemical or a biological process, and for example, methylene urea or urea formaldehyde that have to chemically break down a very large molecule before the nitrogen is in a form that is available for plants, as well as subject to losses. For the inhibitors, stabilizers, we have urease inhibitors that is focused on delaying the conversion of urea to ammonium. Now, we really run into problems with big losses when we have a large flush of urea converting to ammonium. If we can kind of delay that, slow that down, we tend to capture a higher percentage of the nitrogen. And so that's the way these urease inhibitors work. And there's, again, several products here, and I've worked with many of these, and lots of good products out on the market that do what they say that they're going to do. We also have nitrification inhibitors that attack the part of the nitrogen cycle where we're converting ammonium to nitrate. So by doing that, we're trying to prevent the losses from nitrate, leaching and denitrification. When soils are really wet or there's a lot of water moving through a soil, these nitrification inhibitors are particularly effective. And again, several good products, and I've worked with many of these with success. If we look at the comparison of these products in terms of time, it's about 2 to 3 days to hydrolyze urea into ammonium. And of course, that depends on conditions, but roughly 2 to 3 days. And then if we add a urease inhibitor, we then slow that down to more like 7 to 14 days. If we look at the conversion of ammonium to nitrate, that's about 7 to 21 days. And if we add an inhibitor, it slows things down to about 30 to 50 days. And so we're kind of protecting that nitrogen, keeping it potentially in forms that are less likely to be lost. If we do both, we pick up a few more days. We have both a urease inhibitor and a nitrification inhibitor. One product that's a polymer-coated urea, and I've actually done quite a bit of work with this particular one, although I've worked with others as well, is ESN. This is, again, a polymer-coated urea. I'll talk more about that later, but we're getting about a 60 to 90-day release. Now, that's a little deceptive because we get some release almost immediately, and so we get this release throughout that 60 to 90 days. With these inhibitors, that's also true, but it's more of a flush towards the end. So a little bit different in how they react in terms of timing. So let me spend a little bit of time on some of these polymer-coated urea products. I've had really good luck with many of them. And the way they work is we have urea that's coated with a polymer. Water enters inside, it dissolves, the urea hydrolyzes, and then over time, depending on a number of factors, that nitrogen will diffuse through the coating, and then at which point it enters the nitrogen cycle and is available for plant uptake or possibly even a loss. As we look at some ESN prills here sitting on the ground, you can see kind of a variety. This particular one, the urea hasn't even really started to release out of it yet. And this one is completely dissolved. That's an empty polymer coating. And then here's one that's partially done. So that's, again, kind of this timing thing. Some of it releases early, some of it releases later. At the end of the season, 60 to 90 days, everything's released. I want to kind of show some data that helps us understand why we're getting enhanced efficiency with this particular product. And it's similar for all polymer coated ureas that actually work. There are some that I've tested that are really poor and don't work, but most of the mainstream ones that I've tested do work. And so each one of to understand this graph, you need to understand that each one of these peaks represents a day. And so peak to peak is a 24-hour period. Ammonia gas loss increases with temperature, and thus the peak occurs in the late afternoon and then drops off as temperatures cool down. So we're going to look at both ammonia volatilization on the left as well as nitrous oxide emissions into the atmosphere on the right. We've got 4 treatments. The first one is an unfertilized control, which is not zero. There's a natural amount of nitrogen in the soil, and we get some of this ammonia volatilization, denitrification that occurs naturally at background levels. When we add fertilizer, in this case, we're adding a full rate of fertilizer that we would apply to a corn crop. We're applying it as uncoated urea. You can see we get a significantly more amount of loss in terms of these gases. With ammonium, it's about a week after application in this particular study that we saw sort of a peak, and that kind of drops off as the urea and the ammonium kind of moves through the nitrogen cycle towards nitrate. Then on the right, you can see after a couple of weeks, we begin seeing denitrification, and it kind of peaks at about 18 days in this particular study. If we look at a reduced rate of urea, we obviously get a reduced amount of nitrogen loss. And the reason why I'm doing this 2/3 rate is because we have data that pretty consistently shows in several crops that we get similar yields at about a 2/3 rate of polymer coated urea as compared to a full rate of uncoated urea. So for comparison purposes, though, I'm doing a 2/3 rate of the uncoated urea. So we'll compare that to the 2/3 rate of polymer coated urea. And we can see a tremendous drop every day in terms of both ammonia volatilization and nitrous oxide loss to the environment when we're using the polymer coated urea at the same rate as the uncoated urea. We've done several of these studies. I've averaged 5 lab, 4 greenhouse, and 3 field studies where we measured these losses as well as nitrate leaching losses, and I put them on this summary slide. And so the blue bars represent the increase of nitrogen loss when I'm using uncoated urea compared to the polymer coated urea. And this represents about 3 different brands of polymer coated urea in these various studies. But you can see ammonia volatilization is about 300% higher when I'm using the uncoated urea compared to polymer coated urea, for example. Now, when we compare the polymer coated urea to the unfertilized control, there really isn't much difference. So we haven't completely shut it off, but we've more or less stopped almost all of the gaseous loss by using polymer coated urea in a variety of studies. And now, there are some studies, I've done a study where I really didn't see much difference. So conditions definitely impact this. In some cases, you get more loss, in some cases less, as I've mentioned previously. Here's just a visual, a study. I borrowed this slide from another scientist. You can see here on the left, I've got urea ammonium nitrate that was applied, and it was incredibly wet May with a lot of rain in Iowa. And then on the right, you've got a polymer coated urea that was applied, and you can see a visual difference that also resulted in a large yield difference. And here's another one from another scientist, again in corn. different rates. And in this case, though, we're looking at a polymer-coated urea on the left. And on the right, we've got ammonium sulfate. And in this case, we've actually added another enhanced efficiency fertilizer, the DCD, based on that previous slide. That's a nitrification inhibitor. But in this case, we're seeing that there was no, apparently, there wasn't much of an effect. It wasn't really effective to use the DCD. We had other mechanisms in place that this nitrification inhibitor wasn't enough to stop the losses, and as a result, we have massive differences in yield. We have done lots of work in a lot of different crops. Here's some wheat yields out of Idaho. I have some wheat yields. These are another scientist, but we oftentimes see, not always, but oftentimes see some yield increases. In this case, these are some potato trials that I did with various potato varieties over the course of a couple years. In these studies, I actually didn't see any yield increase. The total yield of potato tubers was not statistically impacted by the polymer-coated urea, but the quality of the tubers was impacted. And so what you're looking at here are increases in the US #1 yields over the control. And I've got 3 treatments compared to that control. I've got the GSP, the grower standard practice, applied at a full rate, 100%. And then I've got the polymer-coated urea that was applied at both a full rate and a reduced rate. And over the whole trial, if you look at an orthogonal comparison, the full rate of polymer-coated urea had greater US #1 yields than the grower standard practice when they were applied at the same rate. Incidentally, the polymer-coated urea at the reduced rate, it gave statistically identical yields as the grower standard practice at the full rate. So what we'd like to do is we'd kind of like to be able to match up the nitrogen need of the plant and not leave the nitrogen unprotected in the soil for very long. That would be the ideal scenario. So what you're looking at here is nitrogen uptake timing for potato. Potato is a little unique. It's pretty slow to come out of the ground, takes about 3 weeks. So we're looking at about 40 days before the plants really begin to rapidly take up nitrogen. So if I'm putting on my nitrogen pre-plant or any time in that period, it's really subject to loss because the plants just aren't using it. What we'd like to do is apply that nitrogen again during this rapid uptake period, and it'd be nice if it was kind of followed that same pattern. If that would put the nitrogen at the least amount of risk of loss. So here's some data that I borrowed from another scientist that's also done quite a bit of work with polymer-coated urea, Carl Rosen out of University of Minnesota. And so what you're looking at here is the graph on the left was nitrogen applied as polymer-coated urea at planting versus the other two were applied at emergence. One of them was applied on, in the ground, and one of them is on the surface. So kind of want to focus on that middle graph, middle line. So if we kind of stack these two, what we can see is that if we apply the polymer-coated urea at emergence, we get about the same shape of a graph to match release rates with uptake rates. And again, that would be our ideal world, is be able to do that. Unfortunately, if we apply it at planting, it's just a little bit early, and we have seen some differences. My data is very similar to this data, showing similar results. And then there are other products too. The ESN I was just showing, it has kind of an S-shaped curve of release. There are others like this duration product. These tend to have more of a linear release. So it is important to understand the release pattern. So that ESN matches up nitrogen really well as long as I get the timing right. The duration, this is better. In fact, duration is used mostly with turf grass would be its primary use, but it's also being used in vegetable crops, and so in some cases this product would be better suited for the plants in question. They don't come without their problems. One of the biggest problems we've observed is the polymer coating fracturing during handling. When that happens, you basically get high-priced urea. You don't have any enhanced efficiency properties. We don't have a huge data set, but we have had some experiences. We had one instance where we measured 55% coating failure, which was really a large problem. We had another instance where we only had 5% coating failure rate, but we were able to get it to increase by increasing the speed of the airflow in the spreader and removing some of the cushioning. And so we understand that we do have to be thinking about how these products are treated, how many times they run through an auger, in order to try to avoid fracturing those coatings. So they take a little extra care, and obviously they're more expensive than uncoated urea. We've had other things too. We've had to adjust interpretations. For example, when I use polymer coated urea, we do petiole sampling is pretty common in potato and sugar beets, which we do a lot of work in both of those. And we have measured significantly lower amounts of nitrate in those petioles, which causes growers concern. We've been able to determine that it really isn't a concern, but it's kind of a cultural thing that we've had to deal with in terms of grower adoption. I want to shift gears now and talk about phosphorus. The phosphorus chemistry is very different, and so we need to understand these cycles again and kind of how things work. We don't have to be expert chemists, but we do need to understand some basic principles. And like nitrogen, phosphorus has to be soluble in solution in order for plants to take it up. I always like to say that plants drink their nutrients. So it's got to be dissolved in the soil solution. All of these solid materials that you see around here on this graph, including organic matter or minerals, the plant can't take those up, the phosphorus that's found in those, until it's dissolved or decomposed and in the soil solution. So we talk about the solid phase of phosphorus, and we divide it into non-labile phosphorus and labile phosphorus. The non-labile phosphorus is stuff that is like rock phosphate, that is just very insoluble. It's going to not be readily available to plants in any time in the near future. Labile phosphorus is solid form, but it's more readily available. It's more easily dissolved back into soil solution. When we look at the total amount of phosphorus, there's actually quite a bit in the soil. The average is a couple of thousand pounds per acre, 500 milligrams per kilogram, which is parts per million. When we look at soluble phosphorus, so that's again the phosphorus available for plant uptake, that's less than 1 pound per acre. So a very small amount of the total phosphorus is available at any one time. So through the course of a season, that labile phosphorus has to kind of redissolve in order to supply the plant. When we put on fertilizer phosphorus, it essentially enters that labile phosphorus pool. Some of it stays soluble, but most of it will precipitate back into a solid form, and it is in that labile phosphorus pool. And through the course of the season, we hope that it redissolves so that the plants can take it up. So again, very different than nitrogen. Here's a visual that I really like from a classic study that was done a few decades ago. But if you look at the upper left diagram or picture up here, you're looking at calcite, which is a calcium-based mineral that's in all of our soils, and particularly alkaline soils. And in this one, there's no phosphorus in the solution. And so you can kind of see this unadulterated calcite. As we begin adding phosphorus at higher and higher rates, concentrations, we can see that phosphorus is precipitating onto the surface of the calcite. And so we form these phosphorus solid precipitates. And once again, the plant can't use that phosphorus that is precipitated. And this similar thing happens in soils. And so the phosphorus, if it redissolves through the course of the season, then yes, the plant can get it, but much of it is temporarily rendered not plant available. Another important effect is pH. In this particular graph, the higher we are on the graph, the less available the phosphorus is. We're looking at the extent of retention of phosphorus by the soil. And so the optimum of availability, where phosphorus is the most soluble and therefore the most plant available, is about pH 6.5. If we go to either side of that, if we're alkaline, like most of the soils that I deal with in the Western United States tend to be in that pH 8. And so we have less than ideal conditions for phosphorus uptake. And then same thing happens, although different minerals, but in terms of, we get poor phosphorus solubility in acid soil conditions for the folks who are operating in higher rainfall areas. So do we have enhanced efficiency fertilizers materials for phosphorus? Yes. I will say, though, that I have tested dozens of products and most of them don't work. I tend to be pretty skeptical, but I have worked with a few. One of them that I've worked with that has seemingly good results in some cases is humic acid. I've also worked with other organic acids besides humic acid. Now, I've worked in low organic matter calcareous soils, and mostly in potatoes and sugar beets, but also corn and wheat. And I've fairly consistently seen an increase in phosphorus nutrition under these circumstances. And I'm not going to claim that this works in every soil and every condition. I think it's important to have these tested for each crop and each type of soil. But this is an example of one that seemingly works. So again, we're looking at potatoes. This is my unfertilized control. The study was done over a period of 3 years. Jeff Stark was the primary investigator in this study. I've worked with him on this project. Right. So our one rate of phosphorus was 60 pounds of P2O5 per acre. And then we applied that same rate, but this time we just mixed in a humic acid. Now, this fertilizer was 1034O, ammonium polyphosphate. And so you can see that in each year we had an increase in yield, not always statistically significant in the year itself. Of course, then we have a higher rate as well. Note that rate may seem high for some, but in potatoes, that's fairly common to use those high rates of phosphorus. And then we have the high rate with the humic acid. And so you can see pretty consistently we're getting yield bumps when we apply this. And overall, though, I'm actually getting about equal yielding when I have the low rate with humic acid. If I compare that to the high rate of phosphorus without humic acid, they're it's almost a wash on average. And this is a published study, and there are others who are working with these types of materials. I've worked with another product that's different significantly in how it operates. This product is Avail. I did a meta-analysis with 503 field sites with some of my data, but mostly other scientists' data in a wide variety of crops and studies done all around the world. And we put together this data, and it's really interesting. This graphic really is to me, is very interesting. What we're looking at here is we're looking at soil test categories. So all these studies, different soil tests were done. And so we sort of standardize them by applying them to the IPNI, the International Plant Nutrition Institute. They have categories, and even though that we probably wouldn't want to do that in terms of any individual trial or field, it's helpful in comparing across a whole lot of trials done with different soil tests. So category one over here is an extremely low soil test phosphorus value, and category 14 is extremely high. And what we're seeing here is that we're looking at the relative yield increase when Avail was added to the phosphorus at identical rate. So for example, on average for category number one, we're looking at about a 4% increase due to Avail. And pretty consistently averaged over these trials through these lower rates soil tests, through the lowest soil test values, on average, we're seeing yield increases. When we start getting high soil tests, we no longer have that. And in fact, we are getting some negative results, which underscores the importance of soil testing, that soil testing is a good tool, and that it's not good to be applying phosphorus when our soil test levels are extremely high. But getting back to the Avail, obviously it was making a difference, especially when soil test levels were low. pH, not surprisingly, also had an impact. We had higher yields when we had extreme pHs. The rate of phosphorus also makes a difference. If I have enough phosphorus, if I'm putting on a really high rate of phosphorus, applying an enhanced efficiency product, it doesn't really make sense, because if I have enough, enough is enough. If I have enough calcium in my body, I don't need to take calcium supplements. So if I'm applying enough phosphorus fertilizer to meet the plant's needs, there's no point in adding an enhanced efficiency product. So if I'm using an enhanced efficiency product, I really need to be cutting the rate of fertilizer back. And this it kind of summarizes all of that data. When we look at all 503 sites, we've got an average increase due to Avail of about 2% yield increase. However, when we just look at the sites with low soil test phosphorus, extreme pH, and low phosphorus rate, that jumps up to about 4.5%, which is a good lesson for us to learn, not just for Avail, but for any enhanced efficiency fertilizer product. We need to understand under what conditions it would be valuable to us. Another approach, and again, I'm running out of time, so I'm going to just make it quick, but there is a struvite product that I've worked with. Its name is Crystal Green. It's a completely different approach. Struvite is a material that's derived from waste products, sewage waste. That material is treated and siphoned, and the end product is not water soluble. Like most of our fertilizers that we apply are water soluble. This particular material is not. It's suspected that the mode of action, and by the way, we don't know the mode of action confidently for Avail. I didn't mention that because I'm not confident in discussing that. And this product, again, I'm not 100% sure of the mode of action, but the thought is that it is applied to the soil and it doesn't dissolve. It just sits there until a root reaches it, and at that point, roots exude acids, and then it potentially dissolves the fertilizer material. We've worked with this with a variety of crops. We've had some decent results in things, sugar beets, for example. But potato, we've had particularly good results with. We've had an average of 42 sacks per acre increase in U.S. #1 yields. Again, we don't see that kind of an increase in terms of total yield, mostly the quality and the number of U.S. #1 tubers. So, in conclusion, I think that it's important to realize that we do have enhanced efficiency fertilizer products that work. We also have some that don't. It's important that they're researched by third-party scientists and that we have a high degree of confidence in the product and ideally how it works. In order to use it, though, we really do need to understand these nutrient cycles. We need to understand plant growth cycles, plant uptake rates of these nutrients, ideally mode of action, and or at least the likely conditions for the enhanced efficiency fertilizer to work. And then I haven't mentioned money at this point. Obviously, even if I get an increase, does the increase pay for it? What is my return on investment? And that's always an important factor. If the cost of these materials is so exorbitantly high, in some cases we just can't afford to do that and just apply a higher rate of fertilizer. Now environmentally that doesn't make a lot of sense, but the farmer has to pay attention to the financial bottom line, and maybe society needs to think about providing incentives to protect the environment. But in many cases, these products are affordable, and the yield increases that we gain, or maybe other things can be gains in time of For example, with the polymer coated urea, if I don't have to inject fertilizer every week, that represents a time savings to me. In my own family's farm, that's one of the things that they enjoy the most about that particular product, is that they don't have as much in-season application to worry about. So all that has to be weighed, and we have to make wise decisions. I thank you for your time. I hope this was something of use.